And that was on substitution reactions of alkyl halides in the SN2. I did hear back from Mobius, and there is a way for me to go back and remark questions retrospectively, so we're going to do that. So that's all good. The protein's called SPY1. Anyways, like spy, like the spy with guns and things. So we've talked about this kind of. I'm going to flip through a lot of these because we've talked about quite a bit of these in quite a lot of detail. I'm going to come back to elimination later. We're going to probably later this week, probably on Friday. So substitution, and this actually sums up this challenge we're going to face. You can get something that looks pretty similar. Actually, it's not pretty similar. It's freaking identical. You can get a molecule which can either act as a nucleophile or base. These can actually be the same molecule. In one case, we get a substitution reaction. In the other case, we get an elimination reaction. We make an alkene. So why one and not the other is really the topic of conversation for the next 5 lectures, I think. So in a substitution reaction, a leaving group is replaced by a nucleophilic group. And you can have any kinds of leaving groups. We're going to talk a lot about halogens. I'm going to introduce a few other examples to show you how we can turn other things into leaving groups that aren't halogens. And again, halogens are fluorine, chlorine, bromine, and iodine, though fluorine doesn't really do this chemistry because fluorine makes really strong bonds with carbon, actually. That's the big reason. So what all leaving groups have in common is they are stable. We're going forward on this arrow, which means that, remember, all chemistry is determined by the stability of charged species. So if we want this to happen, that better be happy. Because if that's not a stable molecule, this is not going to happen. So all leaving groups have to be electronegative because they need to create a slight positive charge on the adjacent carbon, which was the electrophilic carbon as we discussed last class. And all nucleophiles need an electron pair. Often they can be charged, they don't need to be, but they do need an electron pair. If they don't have an electron pair, you're not going to be able to do this kind of chemistry. So we've got all sorts of types of reactions. Here we have a list of different types of nucleophiles. These are probably the most common ones. We can have halides being nucleophiles. We can have hydroxides, alkoxides. An alkoxide is like a hydroxide, but with a alkyl group on it. Thiols, or if it's negatively charged, it would be I can never remember what that's called. It's a negatively charged sulfur with an H. It's a negatively charged sulfur with an alkyl group. Thioalkoxide, but that's a really stupid way of saying it. Neutral amines, great nucleophiles. Basic amines, like even better nucleophiles, but also really good bases. We're going to talk about that. Azide, alkyne. We're going to talk briefly about some alkyne chemistry coming up. Cyanide, and notice that's a negative alkyne. It's an alkyne that has a negative charge on one end. It's had a hydrogen removed. Cyanides, if we're having a bad day, a carboxylic acid can do it for us, but they're not really very good because that negative charge is so stable. It's not really all that negative, so it's not really all that reactive. And then we actually saw this with ozone. We saw these triphenylphosphenes, or these phosphorus compounds. So this is all pretty related. They're all pretty similar kinds of chemistry. So I think we discussed this very, very briefly last class versus the SN1 versus the SN2. No, it doesn't. There's not. These are all possibilities, but it's not an order of most reactive to least reactive because it's not that simple. Yeah. So it'd be nice if it was. So So we talked about this last class. We talked about you can have an SN1 or an SN2 reaction. We're going to be focusing on the SN2 in this class. But if you remember that the SN1 nucleophile waits until the leaving group leaves the carbon on its own, makes that carbocation, then the nucleophile comes in, or the nucleophile can sneak up from behind and kick X out. And that's the SN2. And that's what we're going to start with today. And so if you want to visualize this using cats, which is the best way to visualize everything, so consider two cats. I'm at work today, so I don't have two cats in my office. But this actually works pretty well. It didn't work so well with my previous cats because they actually followed a different mechanism because they would cuddle together. But my current cats aren't quite as friendly with one another. And so in the SN1 reaction, you have a cat in a basket. The cat must leave the basket, which leaves the basket in a very high energy state because cat baskets are rarely empty. They normally have a cat in them. And so you can kind of think of as an empty basket as a carbon with 3 bonds. It's positively charged. It's not happy. And the other cat will now enter the basket. And so this is an SN1. The one cat waits until the other cat leaves. Whereas an SN2 is a direct displacement. This actually, I got a question from Bavian saying, does that happen with your cats? Direct displacements do occasionally happen with my cats, normally with cardboard boxes. And so one cat will be in a cardboard box and the other cat jumps into the cardboard box, displacing the first cat. And so this, again, is what's happening here with the SN2 reaction. And notice that the attack is from the back. And so this cat is attacking this cat from the back. There is an inversion of configuration. One cat is off to the right, the new cat's off to the left. And this cat looks actually pretty unhappy. Now, for this to be a stable system, what you need for this to happen in both cases is that the orange cat must want to be in the basket more than the gray cat does. Otherwise, this pattern will run in reverse, and you'll have the gray cat displacing the orange cat. So what we want an orange cat that is unhappy outside of the basket, like a charged species or something that's quite reactive, displacing something that's this cat looks really unhappy. It shouldn't look as unhappy. A reasonably satisfied cat once it has left the basket. And so it's a downhill process. It's energetically favorable. It favors domestic peace to have the orange cat in the basket. So when we think about these mechanistically, and we talked a bit at the end of last class about kinetics versus thermodynamics for these kinds of systems. So for mechanism 1, the SN1, the rate of the reaction is dependent entirely on how fast X decides to leave on its own. It's first order kinetics. It doesn't matter what the concentration of anything else is in the solution. If you're converting X number of moles per liter into a product, the only thing that matters is what's the concentration of that starting material. If it's really concentrated, you're going to have a higher concentration of these things breaking down. If it's really, really dilute, you're going to have a lower concentration because it's really dilute. But the rate of reaction is independent of concentration as far as two molecules bumping into each other. It's one molecule falling apart. Whereas for mechanism number 2, the rate of the reaction depends on the concentration of both the nucleophile and the electrophile because they need to find each other in the rate determining step. And so it's second order kinetics. And that's where these names come from. So again, just doing SN2, we went through this last class, but again, it's a one-step reaction. There is no intermediate. You go from reagents through the transition state when everything's flat, you're attacking the antibonding leaving group carbon bond orbital to form the products. So this is one of those places where Mobius actually has some really nice visualizations of these kinds of mechanisms. And so if you go through your Mobius, you'll see some nice visualizations of these things. And just a reminder, the next Mobius assignment is next week. I was probably as relieved as you guys were that it wasn't this week. So it's next week. And we've drawn these, and this is again this reaction coordinate diagram. And so again, what I want to highlight is these two parameters here, the activation energy, the delta G of activation, and the reaction energy, the delta G of the reaction. And so I'm not quite sure why this graph is showing delta H, because delta G is what matters. But anyways, the how likely I'm exhausted. How likely a reaction is to occur at any given moment depends on the height of this activation barrier hill. At the end of the day, how likely is the reaction to have occurred and how likely are you to be a product depends on the difference, because again, I've drawn this from left to right, but nothing's stopping you going from right to left. Molecules can go both ways. Of course, molecules will want to go down here because it's lower in energy, and to get from here up to that transition state is harder. Sorry, I can't see what I'm doing. Yeah, I'm exhausted. To get from here up to that transition state is harder than to go from here to here, because this distance here is bigger. So it's harder to go backwards than forwards, but it's still possible to go backwards. And that's true with almost every reaction. Yeah, I should take a nap. I'll just go to bed early. I always go to bed early. I wish. You guys make way too much noise out in the corridor. So I'll just probably pop some caffeine pills and run with that. So the mechanism is bimolecular for the SN2 reaction. Both the nucleophile and the alkyl leaving group molecules must collide to form the new transition state. And so the rate law, unsurprisingly, you can actually pull rate laws from mechanism. You need to find a rate determining step. You need to figure out what you need to do to get to the rate determining step, and that determines your mechanism, and that determines your rate law. Like, rate laws are not like some sort of thing separated from theory. I'm just going to make myself yawn. If I turn on the video, everyone will start yawning. So the rate equals the rate constant. This, of course, determines on all the specific details of how reactive is the nucleophile, how reactive is the electrophile, what else is going on in the world, and we're going to talk about that. So that determines the value of K. But this relationship, you can either change the concentration of the nucleophile or the leaving group, and you're going to affect the rate of reaction. Okay, that's clever. Brendan's comment saying I'm going to displace my cats from their bed. That is completely possible. There, to be honest, so on my bed there is room for 2 cats and occasionally a dog and 2 people. The dog's not supposed to be on the bed, but sometimes he gets on the bed if he's being a shit. So, stereochemistry of the SN2, we've covered this. We get inversion of configuration. Again, this is because we are attacking the anti-bonding orbital. Here, what they've drawn is it attacking the bonding orbital, which is just wrong, but the geometry is right. So the anti-bonding orbital, the lobes are switched, right? The big lobe is over here. You can't see because I'm using my mouse on the wrong thing. Big lobes over here, small lobes over here on the anti-bonding, and that's why the nucleophile attacks here. It doesn't attack the full bonding orbital. This is just a shitty drawing by some textbook maker who is wrong. Luckily, our textbook doesn't have this shitty drawing. And this results in inversion of configuration. So again, we covered all this. He's a good boy, Victoria. So almost always talk about my dog. Almost always an R configuration becomes an S or an S becomes an R. But just be careful with how you do that. Normally that's true if if the leaving group and the new incoming nucleophile share the same priority. So if you're replacing a halogen with a halogen, everything else is carbon. Yeah, the halogen is going to be number 1 in both cases. Here, though, the bromine is number 1. It's the heaviest thing. You're bringing in a cyanide. Cool. But the cyanide has less priority than this ether up here because oxygen is heavier than nitrogen. So carbon goes to carbon, carbon goes to carbon. That's a tie. Then it's nitrogen, then it's an oxygen. This one wins. So we switched which one's the most important or the highest priority. And so in this case, they're both S, even though you've inverted configuration. It's just because the rules say the bromine was number 1, now the cyanide is number 2. And so that's swapped our orientation. So in general, an S will become R and an R will become S. You will always invert the stereochemistry. That's always true. But just be careful if you're trying to use that as a clue to try and figure out if it's S or R. Just be a little cautious. So this is where we start getting into the details on this. So steric bulk around the reactive center slows the reaction. So again, our nucleophile needs to sneak up from behind. So if I turn on my video, and let's say I've got okay, let's say we have a molecule like this. Hopefully you can see my video. There's a ring. It's a 5-membered ring. There's a blue leaving group on this carbon and a green leaving group on that carbon. And let's say here's my nucleophile. Here, now it's in the camera frame. So it needs, first of all, it needs to come, this is the wrong angle, right? Because it's coming towards there. It needs to come in from the back. But if this guy's coming in from the back here, you can sort of see that it needs to get to the bottom of this carbon. And there's a problem because look at all this stuff in the way. Like all these things have electrons. So unless I'm coming perfectly, like perfectly on angle, I'm in trouble. If I come in on a slight angle like here, boom, I'm running into these, I'm bouncing off. If I come in on a slight angle like here, I'm going to try and twist this so you can start to see it, I'm bouncing off. If my angle is slightly wrong coming in on the bottom, I've got this big steric bulk of this entire ring here blocking it. And remember, all these things have electron clouds, and this guy has lots of electrons because he's a nucleophile. He's got lots of electrons. That's the entire point of a nucleophile. And his electrons are banging into these electrons, and that looks like a hard center to get to. Whereas this guy, I can rotate that bond. Oh, look at that. That's nice and clear. That's an easy attack. And so because the nucleophile needs to sneak up from behind, you don't want a lot of people watching. You don't want a lot of things attached. So the reaction works best when groups on both the nucleophile and the electrophile are small, right? Because you can add a lot of bulk to this, and then that becomes really hard to get in here if this guy's bulky. And if this is bulky and this is like sterically bulky, it's a lot easier to get to this one. So steric bulk on the electrophile is bad for this reaction. Steric bulk on the nucleophile is bad for this reaction because you are trying to get things in here. So normally let's see if I can find my favorite YouTube video that I can share for this. I did not download it. It saves my search, which I don't know if that's a good thing. Oh, okay. So I'm going to stop sharing for a second because I think this might be the most important part of this course. Share screen 2. So consider this is about the cat door here. Can you see my screen? Hopefully, yes, you can. This cat door here is your electrophile center. This is your nucleophile. It is quite a large nucleophile. And you need to get the angle of attack really, really right. Because if the angle of attack isn't right, your nucleophile is not able to fit through the door. And it is a tight fit. Look, the cat's having a little bit of trouble with this, right? That was the wrong angle of attack to go through that door. So the nucleophile bounces off. Normally it drifts away. In this case, it's licking itself. But, molecules and cats are not quite the same thing. There must be something good through that door. So the cat wants to get through the door. The nucleophile wants to attack. And, well, yeah, but the problem with, Sobavian says the cat needs to lose weight. That's true of me, too. But the nucleophile can't really lose weight because the nucleophile is what it is. But if you get the right attack, the right angle, the nucleophile can get through the door. So we do need the right angle between the nucleophile, and the electrophile. The electrophile is a small target, and you need to hit it. I'm going to share my screen. And the nucleophile can be quite large. And so, and compare that, I would say that that's, you think, oh, that must be a really big nucleophile and a really small electrophile. That's actually kind of a good case scenario. The nucleophile only needed 2 tries to get through that electrophile door. You're kind of actually just barely able to squeeze this thing through most of the time. So unsurprisingly, the bigger the door or the smaller the nucleophile, the faster this reaction goes, the faster you get the cat through the door. And so the SN2 reaction depends on the leaving group, on the R leaving group, the electrophile. So an electrophile that's only a methyl group, that doesn't have a lot of hindrance, has a huge door. If you have a primary carbon, it's a slightly smaller door. A secondary carbon, we're getting pretty small. This one probably approximates a primary carbon, but we're going to get smaller with a secondary carbon. The door represents the electrophile. That's the target. That's where we need to get to. That's where the cat's the nucleophile, the door is the electrophile, and it's the angle that we need to hit to displace the leaving group. So the cat needs to get through the door at the right angle. So depending how hindered that door is, depending how skinny that door is, depending how much stuff there is blocking the entrance to the door, the harder it is. So if we say that this one is a primary, you know what? Oh, I stopped sharing. Okay, I'm going to start drawing. Here's the door. Oh, you know what? I'll draw under here. This was the one in the video, was a primary. You know, a methyl is big. There's lots of space. There's nothing getting at, and there's a cat. It's got ears. And there's no problem getting this cat through that door. And this cat is the nucleophile. Now the door's gotten smaller. Cat can get through the door if it does the approach right. Door has gotten even smaller. Maybe not quite that small. And it's really good that cats are liquids and they're very compressible. And eventually, this cat will squish through this secondary leaving group door. But the door is quite a lot smaller now. And now for the tertiary, no matter how small your cat is, that door is not going to be able to get a cat through it. So tertiaries do not do SN2s. Door too small. Even for a liquid cat. There. It's in red. I'd put it in red again, but tertiary leaving groups, like this guy here, do not do SN2 reactions. They just don't. So if we try and do SN2 conditions, we throw in a cyanide, we've got a molecule with 2 leaving groups. So let's just identify things again. The bromines are our leaving groups. How do we know that? Br minus is a stable molecule, so it can leave. That makes this carbon and that carbon are electrophilic carbons. This guy is our nucleophile, and if I draw the Lewis dot structure of it, there's a formal negative charge on the carbon, and not only is it formal, it's real negative. That carbon's got 8 electrons and a lone pair. It doesn't want the lone pair because it's carbon. So it wants to react. This is our nucleophilic atom. And now SN2-like, it cannot attack this one because this is tertiary. That door is too small. This is a cat. It's a good cat. It's not even a very big cat. But an SN2 door is just too small for any cat. So the only possible reaction is at the other leaving group. Okay. Now, this is where we start getting into details. And yes, it would proceed by SN1. We're going to get to that. Manuel asked, would the other one proceed by SN1? The answer is yes. Yes, it would. So, solvent effects in the SN2. Aprotic solvents increase the reaction rate. So, aprotic solvents are solvents that do not have a hydrogen atom that can make hydrogen bonds. So, they don't have a hydrogen atom on a heteroatom. Their hydrogen atoms are only on carbons. So, you can't get the hydrogen bonding interaction. Now, why does this matter? Well, let's think about a strong nucleophile, like fluoride, F minus, in a protic solvent. It's going to be surrounded, in this case, it's some alcohol. It's going to be surrounded by hydrogen bonding to the fluorine. What are we doing with that? Well, we are delocalizing that negative charge. It is making bonds with those things. The fluorine is becoming less negative because of that. That's a good thing. We want to make things less negative normally. The problem is if we want this to react, what we've just done is we made it less reactive because we've made it less sharp. Like a full negative charge on one fluorine is very, very sharp. It's got a nice, well, you know what, this actually isn't very sharp. It's a dull stylus kind of thing. I normally have a knife in my office, but I don't currently have a knife in my office because knives are sharp. But, you know, if we want it sharp, but the problem is when you hydrogen bond it, you take away the sharpness, you make it much more dull. Like, that's not as pointy. It's not as likely to stab through human skin and displace the leaving group. And so with a protic solvent, we're removing the sharpness because we're attenuating the negative charge, so we're making it less reactive. Whereas if you have an aprotic solvent, you can't do this. Something like an ether or an acetone, it can't make the hydrogen bond with the fluoride. So the fluoride remains sharp, it remains naked, it remains unclothed by the surrounding solvent, and it remains a lot more reactive. Like, it's kind of like, you know, it's a lot sharper if I have the, if I remove the protic solvent. Now, we've talked about the electrophile, we've talked about the solvent, the nucleophile. The stronger the nucleophile, the better the reaction. That makes intuitive sense. The more reactive one of the components is, the more stronger the reaction. That's basically exactly what we just said. The solvent decreases the reactivity. A protic solvent decreases the reactivity of a charged species. So a more reactive charged species is going to react faster than a less reactive charged species because it's more reactive. And what does more reactive mean? It means less happy. It means it really doesn't want to be being in the state it's in. So, as a rule, a species with a negative charge is a stronger nucleophile than a similar neutral species. Notice I say similar is big key here, because you can sometimes have, like, iodide, I minus, is not as good a nucleophile. Well, no, it is. Okay, F minus is not as good a nucleophile as an amine, even though F minus is negative and amine is neutral. But if you're ever comparing a negative charge to a neutral charge on the same atom, the negative is going to win every single time. Much more nucleophilic. So nucleophilicity decreases from left to right in a periodic table. And that makes sense. Let's think about the charged species. Would you rather have a C minus or an F minus? And you'd rather have the F minus. The F minus is more stable. So as you go further right, negative molecules stabilize negative charges better, so they become less nucleophilic. And even when you don't have the charged species, you see the same effect in a neutral species, because once they do the reaction, they're going to become positively charged, and you'll see the opposite effect. A nitrogen stabilizes a positive charge better than an oxygen, and so nitrogen is more likely to become positively charged by attacking a carbon than oxygen is going to become positively charged by attacking carbon. And so I need to show an example of this because otherwise I just feel like I'm saying words. So if the oxygen attacks that, or if the nitrogen attacks the same molecule, the initial product of this, and this is, you can start to think of this as being related to the transition state. I'm not drawing a transition state though, I'm drawing an intermediate. The transition state is when the iodine bond is breaking, the oxygen bond is forming. I'm not drawing that, I'm drawing kind of an intermediate. But the intermediate's energy is related to the transition state's energy. And if I'm looking at that versus that, this guy is more stable because N plus is more stable than O plus, which means that NH3 is more likely to react than water because I can make a more stable molecule. And then we see the same thing in a second row. So basically all this stuff follows rules for electronegativity. It's not surprising. It's actually exactly the same rules. Things that are strong bases are also strong nucleophiles. So when going across the periodic table, nucleophilicity parallels basicity. Now, size is where we get a little weird. Nucleophilicity increases going down the periodic table because of an increase in size and polarizability. So fluorine is small. Fluorine tries to make a bond with something. Yeah, it can throw 2 electrons out on this side, but can't really throw 2 electrons out on that side. It doesn't get them all that far out from everything else. Whereas iodine is very big. It can do a lot of bonding. It can easily have a very negative side of the molecule, give it some direction. Because there's so many electrons, the extra electron being really well defined on the right-hand side of the molecule is very possible. So we have here sort of a table of strengths. And we're not going to try and define them in terms of absolute relative strengths in amongst each other, though I guess we could do that. We have here sort of 3 groups. We've got strong nucleophiles. Note that what we have is things like phosphorus, which is just very, very nucleophilic because the P plus is very stable. And then everything else is basically like negatively charged sulfur, negative charged iodine. Amines can be neutral and still be very, very nucleophilic. Because again, like phosphorus, nitrogen stabilizes a positive charge nicely. But if we want a strong oxygen nucleophile, we need to make sure it's deprotonated. Moderate nucleophiles, I definitely agree with chlorine belongs here. I think bromine's kind of right on the fence between strong and moderate. We're going up the table from iodine. Iodine was big. It could make sort of that, it's like an amoeba sticking something out and poking things. Iodine's better at it because it's a bigger amoeba than bromine or chlorine or fluorine. So bromine's kind of in the moderate space. Then we have ammonia. Now, note that you have an NH3, you've got nitrogen here. Why are these different? Why is this one moderate and that one strong? And again, that comes down to hyperconjugation. So if we just think about that, NH3 goes back and forwards, H plus to NH4 plus. You know what, I'll make this into R plus. We'll make it just like this case, NH3R versus NHR2. It already has 2 alkyl groups on it. And what we have here is we have 3 alkyl groups donating electron density to that nitrogen. Because carbons can donate by that induction and by hyperconjugation, whereas hydrogens can't. And so it's better to have multiple carbons on a nitrogen instead of multiple hydrogens to stabilize a positive charge. So that's why, because this guy will stabilize a positive charge better than this guy, I'm going to just write that, stabilizes positive better than ammonia. then yes, I think that's the end of my thought. Um, a neutral sulfur is in the middle. Chlorine, again, like bromine. Again, we're going up the halogen table. It's not as good as bromine, but it's okay. Then we have something like a carboxylic acid. It's charged. It's an oxygen negative, but oxygen negative is really moderated by resonance. It's not a full negative, so it's not as reactive as like an alkoxide. Then we have the weak nucleophiles. Fluorine is a weak nucleophile because it's not very polarizable. Yeah, anyone who's got to go to the lab, bye. This is all going to be recorded. It's going to go up late, so you can watch the last 20 minutes. 10 minutes. Yes, 10 minutes on your own time. Then we also have neutral water species and neutral oxygen species. Again, not very nucleophilic because they're not very charged. They're pretty happy as is. There's no real reason for them to react. Okay. For the SN2, the better the leaving group, the better the reaction. So on the electrophile, the more stable the leaving group, the more reactive the molecule. And so leaving group favorability is entirely determined by how stable the thing is once it leaves. I minus is pretty stable. We've talked about this. Iodine does a really good job stabilizing that negative charge. It's better than bromine, it's better than chlorine, it's better than fluorine. This is better than a carboxylic acid, where you have resonance stabilization of the oxygen. This is better than hydroxide, where you don't have resonance stabilization of the oxygen. This is a better, more stable thing than an alkoxide, where the R group, the alkyl group, is trying to donate electrons to the oxygen, but the oxygen already has too many electrons, and that's not happy. And this is much better than the mean because N minus just sucks. And no, we don't even bother writing where C minus is. It's worse. It's kind of off the side of this thing. It's just a horrible leaving group. So the weaker the base the anion is, the better the leaving group. And so that makes sense because a weak base is a stable negative charge, and we want stable negative charges. So anions with strong conjugate acids are the best leaving groups, and that's exactly what we see here. And that's because what a strong conjugate acid means, if you're a neutral conjugate acid like sulfuric acid, you have a really weak conjugate base. And it's the conjugate base, it's the weakness of the conjugate base. It's how stable the conjugate base is that determines that you're a strong acid. So we have a little table of what's important for SN2s. Good leaving groups, that's good. Accessibility, low steric hindrance, we want to be able to get at that center, so we want nice big doors. We want a nice strong nucleophile, so what we want is a hungry cat that really wants to get through that door. And we want an aprotic solvent, which I guess means that we don't want to be sort of stabilizing that cat. We don't want treats scattered on the side of the room, because if we have treats scattered over here, the cat's not really all that interested to go through the door because it's kind of stable. We want a hungry cat, and so we want aprotic environment, which means no treats. And this results in an inversion of configuration at the center. So we can think about this with a few possible example problems. We'll run through a few of these and then call it a day. So if we have an example like ethyl iodide with sodium cyanide, the first thing you need to do, if you know it's going to be a substitution, we're going to get into when you don't know it's going to be a substitution, but if you know it's going to be a substitution, the first thing you need to do is you need to figure out, where's my leaving group, where's my nucleophilic atom, and where's my electrophilic atom? Well, my leaving group is the iodine. That means that the carbon attached to it must be my electrophilic atom. This is just cyanide. I'm just going to rip away that sodium. Whee, sodium's floating away somewhere. That means that this carbon is the nucleophilic atom because it's the one with the negative charge. So we've identified the nucleophilic atom, the electrophilic atom, and the leaving group. Now we just draw an arrow from the nucleophilic atom to the electrophilic atom with the leaving group leaving. I don't have any concerns about stereochemistry here because this is not a chiral center. So yeah, it happens with inversion. It's just you can't tell because it's not an asymmetric center. So, I like this question. Rank the following compounds in decreasing order of their reactivity towards the SN2 reaction with sodium methoxide and ethanol. So which one's most reactive, which one's least reactive? Sodium drift off, it's sodium iodide. Yeah. It's spectating. It just, it hangs out. It's still there. It did nothing. Who cares? This course is all about sodium abuse and neglect. No, not really abuse, just neglect. We just don't care about sodium. So we're going to keep not caring about sodium. And so what you want to figure out is which of these reactions is fastest, which one's slowest. And maybe the first thing to do, if you're not sure, is draw out these molecules. So those are your 4 alkyl groups that we have here. We haven't really seen too many terminology for tert-butyl and isopropyl. But I know a lot of you who did focus on nomenclature in high school, I'm sure remember tert-butyl and isopropyl. But if you don't, that's what those mean. And so now the question is, okay, which one of these is fastest? Now, our solvent is the same. So we're not changing solvent. So we don't need to worry about solvent. Our nucleophile is the same. So we're not changing nucleophile. We don't need to worry about nucleophile. All we have here are different electrophiles. And what we see is we've got sort of 2 things that we're varying. We're varying the leaving group, iodine or bromine, and we're varying the steric bulk. So I'm going to give everyone, take a minute, try and think of your order going from most reactive in this family to least reactive in this family. Okay. So the one thing that was in red earlier in this lecture was tertiary carbons do not do SN2s. I guess so. It says decreasing order of reactivity. So least, no, that makes it 4. Yeah, least reactive. Because it's tertiary. It's not going to react. Okay. Now our most reactive, we probably want the best leaving group and we want the less, exactly. We got somebody calling for Carly calling for methyl iodide being the most reactive because it's the least sterically hindered, tied with methyl bromide, but you got an iodine leaving group instead of a bromine leaving group, and the iodine's a better leaving group. Number 1. Now this is just direct one-on-one comparison, less hindered than that guy. So we can come up with this order. And it's because we're looking at both the nature of the leaving group and the nature of the electrophilic carbon. So in this case, let's predict which one's going to be the stronger nucleophile. The second one's easier than the first one. strong nucleophiles don't want to be what they currently are. They want to react. So basically, the question is saying which of these is most reactive. And you got a negative and a neutral thing, and they're going to react by donating electrons. H2S is a terrifying gas, really, really toxic, so not great. Although, so is phosphine. Phosphine is great because it catches fire in air. And so if you're comparing these two, we're going down the periodic table from nitrogen to phosphorus. And as you go down, you become more nucleophilic. Just like with that iodine being more nucleophilic than fluorine. So there are more practice problems available. I've uploaded another assignment, which has more of these. I've actually uploaded, I think, the balance of the assignments. I'm going to come up with an assignment on carbonyl chemistry. I don't have one, but I'll steal one and make one. What was the last one? Oh, sorry. My computer closed, or maybe yours. I'm not sure. Maybe mine. The phosphine is more reactive than the ammonia because as you go down the periodic table, you become more nucleophilic. Iodine, again, because your electrons can be more pointy because they're further out. So iodine is more nucleophilic than fluorine. So these are some good. These are actually good practice problems. I actually like the ones in the textbook, and I think this is actually where the textbook does pick up. And then we have more again in the assignments as well. There's also a practice exam posted. I got a couple questions about the practice exam. Are we going to have multiple choice on a real exam? I hadn't actually thought about that, but we might. I will let you know with plenty of notice what's going to be, what kind of style of things. Mostly it's going to be drawing and short answer. I prefer avoiding multiple choice because I feel with the Mobius assignments, I think you've seen all the multiple choice you ever want to see in your life. And so we're going to try and move away from multiple choice for the final. But I might have a small amount of multiple choice. The practice exam is on Blackboard under assignments. I'm just going to check and make sure it's there. Yeah, practice exam. There's assignment. There's assignment post assignment 4 and 5, 3, 4, and 5 maybe, and then there's a practice exam as well. So yeah, it's under assignments. Okay. I don't know how many questions the final will be. I think the practice exam is probably a good. This is under H2 and H2, bottom of last slide. Most and least. Or maybe I should write stronger and weaker, because that's the terminology used up there. Do you need to write stuff in? Yeah, you will in your final, and that's gonna be good because you're gonna get part marks, and we're really gonna test if you understand this instead of just get the right answer on a Mobius kind of thing. Okay. Thank you, everyone. Have a really good rest of the day. I'm gonna go have a nap with some cats. Maybe do some SN2s, and yeah, I will see you later. Take care. Bye.